Hello, everyone. Olá a todos presentes aqui nessa sessão. I think it's a pleasure to be here with many people that we know for many years. Others we know only today. First time, but it's very important we meet each other. É um prazer estar com pessoas que a gente conhece de outros tempos, mas é muito importante nós estarmos juntos aqui. So we are going to have a session number 3 of the Brazilian Symposium for Computer Music. So nós teremos agora a sessão de número 3 do Simpósio Brasileiro de Computação Musical. I hope we have a nice time to see what people are engaged to produce music with computer. Eu gostaria que vocês ficassem felizes de saber aquilo que as pessoas estão fazendo usando o computador para produzir música. Então, vamos ao primeiro paper dessa sessão. We're going to have the first paper of this session that's called the Applications of FFT for Timbral Characterization in Woodwind Instruments.
Hello, everyone. My name is Yubiri Gonzalez, and I'm going to talk about application of FFT for timbral characterization in woodwind instruments. To characterize sound in general, and musical sound in particular, it's necessary to know the attributes of pitch, intensity, duration, and timbre. Timbre, however, is a multidimensional and briefly defined attribute that make it possible to distinguish between different sounds even when they have the same intensity, duration, and pitch. This paper aims to propose a set of acoustically motivated timbre descriptors that allow the computational extraction of timbre information for the automatic identification of woodwind musical instruments. The audio record of the earphone were obtained from the TinySoul open source sound library. We obtained the FFT for each audio, and the calculation of the coefficient was performed on the frequency spectrum of the fourth octave. Musical frequencies make up a set of only 12 different values in the fourth musical octave. Therefore, in a first approximation, musical timbre can be characterized by a limited set of dimensionless quantities related to frequencies and amplitude in the spectrum. The affinity coefficient describes how far the spectrum is from the ideal case, that is, how far the maximum principal is from the mean value in frequency or centroid. The affinity coefficient allows discriminating different sounds with the same centroid. We can see that different musical instruments have different amplitude in their fundamental frequency. This motivates another descriptor, the sharpness coefficient. Ideally, the sharpness coefficient is equal to 1 in a pure sound that would have a single maximum, without secondary frequency. We can see that the variation of the sharpness of the earphone in the fourth octave. It's observed that, in general, the clarinet is sharper than the transfer flute and is sharper than the bassoon. In general, the identification of musical instruments can be made from the spectra of the presented FFT spectra for the fourth octave record. This discrimination regarding which harmonics are presented or absent is not univocal. It presents the degeneration, and the same for that for some musical sound, two different earphones present the same harmonics. The next coefficient evaluates how harmonic the partial or secondary frequency in the FFT spectrum. We can see that the quality of harmonicity varies with the musical note and instrument. So for the characteristic sound of referent A4, the bassoon and clarinet are completely harmonic, and the transfer flute is completely harmonic also for C, D, E, and A sharp. The fast Fourier transform allows analyzing digital audio record on the temporal musical scale, generating a unique spectrum that characterizes it. It's possible to calculate oversight coefficients that reflect timbre characteristic of the fundamental frequency and harmonic distribution in the FFT. Thus, the proposed timbre descriptor, affinity, sharpness, and harmonicity allow distinguishing the timbre of instruments. The spectral signature of the Goodwin earphone, which allow the univocal identification of them, can be obtained through the FFT by the distribution of harmonic present outside the lower range of the fourth octave. Future work will implement the FFT technique and the described timbre coefficient on the completing the tessiture of the selected earphones. Thank you very much for your attention.
So is there any question? I may ask a question, okay? You have used three descriptors: affinity, spectral affinity, and harmonicity. It's not clear to me why you decide by these three ones and not and don't use another one. What makes these three efficient for your proposal?
Boa tarde. Esses primeiros três coeficientes, têm eu queria demonstrar o mínimo possível de coeficientes para classificar ou identificar instrumentos musicais dessa família de instrumentos, né? Então, esse primeiro conjunto, ele apresenta uma descrição do máximo central, nesse caso da frequência fundamental. A ideia agora, nos próximos trabalhos, é explorar conjunto um pouco mais, outros coeficientes, além desses três apresentados, para agora obter o análise da distribuição global, incluindo a frequência secundária. Nesse primeiro trabalho, nós queríamos encontrar o mínimo para classificar e com essas três e a signature, a assinatura do timbre, poderíamos classificar e identificar instrumentos musicais.
There's another question here from Sérgio Freire. Did you use sounds with diverse dynamic levels for this evaluation?
Nesse primeiro trabalho apresentado, não usamos variações da dinâmica, mas pensamos incorporar em próximos trabalhos as variações da dinâmica e a completar toda a tessitura dos 4 instrumentos estudados.
I want only to emphasize that aspect that Sergio Freire asked you, is because when you change the dynamics of the instrument, you change, in many instruments, you change very much the timbre. So that means it's very important that you take in account the variation of dynamics. I think is that what Sergio Freire wants to tell you, I guess.
Sí, so, vamos incorporarnos.
You have seen, for example, experiments from Jean-Claude Risset with brass instruments. When you change the dynamics, you change a lot the spectrum. So sí. Is there any other question? I think we can go for the next one. Real-time qualification of percussive sounds based on correspondence between Schaeffer solfeggio and the low-level audio descriptors.
The main motivations of this work are, first, the fact that the solfège proposed by Schaeffer is very adequate to approach percussive sounds. Second, the perceived similarities between the use of low-level descriptors and the practice of reduced listening. And third, the will to work with percussion in interactive situations. Here we show the main settings used in the program, including those related to pre-processing and segmentation routines. They are detailed in the paper. The implemented descriptors can be classified as belonging to the time or frequency domains. In the time domain, we use the proper waveform and different envelopes to estimate the features listed here. In the frequency domain, we use spectral peaks and fundamental frequencies to generate curves for each of the listed descriptors. Each curve goes through a simple statistical analysis. The combination of these descriptors can cover most aspects of the Schaefferian criteria. This table depicts the intended correspondences between Schaefferian criteria and attributes and the low-level audio descriptors. Our examples are dedicated to attack profiles, allures, mass, and harmonic timbre. After showing the max patch in work, we depict some numerical results. The attack profile is a curve of a maximum of 300 points, which represent 400 milliseconds that builds up just after the onset. For example, I slap on a tambourine. Here we have the results of a simple statistical analysis of this curve: temporal, centroid, and spread, skewness, crest, and flatness. Another example: I jeté on a berimbau. Another one: a gyro slide. This table shows the results of a statistical analysis of 8 attack profiles. An abrupt attack marked in yellow presents low temporal centroid and spread, positive skewness, high crest. In green, it's possible to see that a steep attack has some similarities with the abrupt one, but with a larger temporal spread and a shorter crest. An esforzando, as shown in light red, has a large temporal centroid, a negative skewness, and a small crest value. Schaeffer considers the allure as a generalized type of vibrato. These descriptors are able to indicate their presence, regularity, duration, depth, symmetry, and spikiness. Using Parseval's theorem, We calculate the number of partials needed to express 50 and 80% of the sound energy. The most prominent spectral peak and the spectral centroid are also plotted here. Some examples: an untuned gong, a thunder shake, It is also possible to compare the sound of a drum with snares and without snares. To identify different classes of mass, we use a combination of descriptors: the ratio of unpitched to total frames, and the number of partials needed to express 50 and 80% of the sound energy. Tonic or pitched sounds in yellow have a small ratio and a small number of significant partials. In a similar way, we can use the same set of descriptors to estimate attributes related to the harmonic timbre. Concluding, we consider that we have taken the first steps to associate low-level descriptors and Schaefferian criteria in the field of percussive sounds. Our future work includes the characterization of different profiles and the interactive practice with percussionists.
Thank you. Great work. So is there any questions? Okay, Sérgio, Zé Padovani, Caio, congratulations for your work. So if nobody's do any question, I make my question. I'm very, very much curious because you did something I would like to do myself. So I congratulate you because it's something I do love to have. So, but I guess, as I know you a little bit, that we're going to try to use that in a kind of creative approach. So since you haven't using them in real time, could you comment, is there any chance to use that in composition or any application like that?
Yeah, that's the main idea, is to use it in real time to make a kind of solfege of what a musician is playing. And then with this information in hand to propose some dialogue, based on this criteria. So the descriptors are not very complicated to run in real time.
And also it can be also a way of signalize to the computer what the percussion is doing, the percussionist is doing, but also is a way of giving to the computer some autonomy to decide or to in terms of sound processing and so on. Very, very interesting. Is there any question?
Hello, Professor. Did you try to make some representation combining more than one feature to represent the sound?
For each criteria, there is a combination of descriptors that will go through a machine learning process, and then we got a label about that. So I think there are too many combinations, probably. So we prefer not to parameterize it, but to give it to a machine learning algorithm.
Okay, thank you.
So is there any other question here in the room or in the YouTube? Okay. Thank you, Sérgio, Zé Padovani, Caio, for the beautiful work. I enjoyed it. So let's go for the next material. The next presentation is a roughness model implementation to analyze sound mass composition, a case study in Liget's continuum for harpsichord.
Hello, my name is Mikael Antunes and I will talk about the paper A Roughness Model Implementation to Analyze the Sound Mass Composition, a case study in Liget's Continuum for Harpsichords, written by me, Guilherme Fiolo, and Jonas Manzoli. We present in this paper an implementation of a roughness descriptor based on the model of Pantelis Vasilakis. We use the implemented descriptor to carry out a computer-aided musical analysis of Georg Liget's Continuum for harpsichord. Our musical analysis established a parallel between the roughness model, concepts of sound mass composition, microtime perception, and Liget's idea of timbre of movement and permeability. Sound mass composition aims to achieve the limits of the perception by exploring a large agglutination of sound in time and frequency domains. Continuum's score has only one rhythm, and the variation in the piece sound result comes from the variety of the melodic profiles and patterns written by Liget. The musicological interest of the Liget's continuum resides in the manner that the constant patterns of the score lead to the emergence of sound mass perceptual characteristics during the performance. An important characteristic of the sound mass is their microtime behavior. Therefore, we may understand roughness as a representative feature of the microtime perception.
The roughness model used in this work was proposed by Vasilakis and is linked with the critical bands concept, which is anchored in the modeling of the basilar membrane. Function R computes the roughness for two tones with frequencies F1 and F2 and amplitudes A1 and A2. The roughness for a complex sound is then computed for all combinations of its partials. To conduct our analysis, a roughness descriptor was implemented in Python. The main steps for the roughness computation are displayed in the pseudocode and involve frequencies and amplitude computation via short-time Fourier transform and roughness computation for all pairwise frequency combinations.
We could associate the concept of sound mass with the principles of minimum masking and limited density, both related with the behavior of the basilar membrane. Start from this point of view, we argue that the roughness model will provide a one-dimensional representation that will reflect the following characteristics: the density level and agglutination of the spectra in the frequency domain, and the perceptual features related to microtime amplitude fluctuation.
Our analysis was divided in three steps. First, we applied the proposed descriptor to extract the roughness values from the chosen audio recording. Second, based on the roughness levels, a segmentation of the piece was proposed. Finally, we combined the data obtained from the last two steps with the musicological concepts previously presented.
Let's now talk a little about this figure that represents the roughness behavior in Liget's continuum. The blue line represents the roughness and the orange line represents its moving average. The dotted line is a segmentation of the piece based on the manipulation of the tension of the sound mass through the roughness. Second, in terms of the development of the material in time, a kind
So I think we have a technical problem. I can see everybody here, but we have a problem with the video. Let's see again if it works now. Are you going to try again? Mikhail, do you want to say something about this slide? So you can say, because everybody can listen to you.
So, we can... A gente não vai esperar o vídeo, então, voltar. Tá bom.
I think, I don't know.
Ok. Mas a live tá rolando? Essa que é a minha questão também, porque ele tava no...
May you can, we can leave this image and you comment to finish your presentation.
So, okay.
You can continue. Okay. Let's go. How about we come back here and we keep this image and Mikhail comment the last slide, and we go for the question sessions. How about it? I don't know. Okay. Mikhail, maybe you can finish your presentation and we move for the question session.
Okay, I can share my screen if it's possible also. Okay. But the main idea of the analysis, we found in the analysis some patterns in terms of roughness when we analyze the ligates. We see some profile, increasing, decreasing profile, and by observing the minima of the curve, we can segmentate the pieces. It's interesting to note that when we analyze the ligates continuum from a psychoacoustic perspective with the roughness model, we can see some similarities with segmentation with symbolic score. But we perceive that we have some patterns in the score which leads to different patterns in the roughness score. So I can share the screen here. Okay. Well, this is the main idea of the piece. We can understand also at the same time we have this profile of roughness with increasing, decreasing. We have also an overall the piece a decreasing profile, which suggests a kind of filtering process during the ligate piece. We want to tell that it's not a simple task to measure the roughness from the audio, because we have some characteristics of the FFT, and we need to improve some of the descriptor by working in the FFT algorithm. For example, with the techniques of peak picking. And we also understand that we need to verify in more detail the characteristics of the audio in comparison with the characteristics of the instrumental, the score of the ligate. So I think is that I'm a little nervous because of the presentation, but we can talk more about if you have any question.
I may complement is that I think it's very important to say that this roughness descriptor that you are using, there's some collaboration between yourself and in adjusting these, because many of other approach that analyze ligates continuous based on the symbolic score. That means the people are using to analyze, having a look on the notes. So that's when you approach this with roughness, we are trying to combine what is already done in terms of literature about ligates with another view that's in combination can give more, let's say, no more precision, but more idea what's happened when we are listening to the continuous. Everybody knows that when you listen to continuous, you have these very much measured sounds that are very much intriguing because they are connected in the way the sounds are mixed with each other. And the idea of this analysis is to try to give some lights for that intriguing psychoacoustic effects that we have when you listen to ligates continue.
Yes.
I have one question for, and that's it. This roughness is very different from this intrinsic dissonance by Setares. Have you tried both? Or that's the one I use, and we use it with the spectral peaks only. I think that it's an idea that you are thinking about, not to apply to every beam of the FFT, but to some selected spectral peaks, which will have a more precise frequency also.
Mm-hmm. Yes, we are using the model from Vasilax. The Vasilax model is a review of the model from Setares. But the most difficult issue is not the roughness model. It's precisely the FFT, because when we make some tests, we see that if you don't have a good FFT parameters, you have a lot of a more higher value of the roughness because of the great quantities of frequencies of the beams, etc. So in our algorithm, we are using picking techniques to take a more sharp spectrogram.
Oh, thank you.
So actually, you're trying to improve the Vasilax model by using that. So that's also is a contribution of your work. That's has to be said, because and that's important because it was the most difficult thing. That's the question of Serge is very important because it was the most difficult thing you have to confront when you are evaluating and developing the algorithm, isn't it?
Yes, this is the issue, and you have to think. I don't know because for example, in the case of continuous, we have the harpsichord with a lot of attacks. If you have, for example, when we try tests with the wind quintets, we have other characters from audio to do. So this is a ongoing process with this descriptor. I don't know if you have the best solution until now. It is important to talk that it is a collaboration with the fellow from WIMI, from the Computational Institute.
So, mais alguma pergunta? Okay. So, if there's no other questions, we go to the next paper. That's concatenative sound synthesis as a technomorphic model in computer-aided composition.
Hello, the name of this research is Concatenative Sound Synthesis as a Technomorphic Model in Computer-Aided Composition. The authors are me, Júlio Guatimozin, José Henrique Padovani, and Carlos Guatimozin. The main goal of this research is the exploration of the mechanism of concatenative sound synthesis as a process for instrumental notation based on the concept of technomorphism. Concatenative synthesis may be roughly described as follows. It is a digital signal processing technique which has two main inputs, a database of audio samples and a target sound. These audio sources, both of these audio sources, are segmented into small audio units and then analyzed by a set of audio descriptors. We then measure the correlation between the feature vectors extracted from the database and those extracted from the target sound. The output is the concatenation of the database fragments with the highest degrees of correlation into a synthesized audio. Here is an example taken from the Pure Data Library Timbre ID developed by William Brandt. Here is the target sound.
The sounds as they appear to you are not only different from those that are really present.
And here is the synthesized audio having a database of an audio of a string trio. On the other hand, technomorphism is the metaphorical use of a technological process applied in a context other than that in which it was conceived. In our case, we want to transpose the mechanism of concatenative synthesis from the electroacoustic music context to the instrumental music context. To do so, we developed a technomorphic model of concatenative synthesis. It is in some degree similar to the original implementation of this technique, but it has some adaptations. It also has two main inputs, in this case a database of percussion samples and an electroacoustic landscape, which is our target sound, and it sounds like this. Both sound audio sources are segmented, but our segmentation procedure is a bit different from the original one. We first identify sound objects within each audio, and then we split each sound object into a transient and a decay sustain release fragment, TRAN and DSR. Here are some transient fragments identified in the target sound. And some DSR fragments. Each one of these segments are analyzed by a set of audio descriptors. In this experiment, we used 13 MFCC's coefficients and 1 RMS coefficient. We then follow to the selection by correlation procedure, in which each TRAN and DSR fragment of the target sound is correlated to a segment of the database of the same kind, transient or DSR. We then produce an evaluation test to see how the database samples fragments were sequenced in this process. And the output is the transcription of this evaluation test, which is the symbolical representation of the selected fragments of the database in a music score, considering their respective duration, instrumentation, and technique. This is one result that we had. This is a raw music score. This is the music score that the algorithm returned. It has no human interferences. Here you can see the instrumentation that composed the database. The generation of these types of scores may contribute to several instrumental composition processes by proposing gestures, textures, and instrumentations which a composer may then manipulate or build upon in order to develop a creative process. That's it. Thank you very much.
Oh, it's very nice work also. So any questions?
I had one doubt because when your source landscape, the sounds are very dry, not very resonant. And when you played the result, there was a big cymbal. It was a big resonance.
Yes.
That was
okay. Yes. We planned this soundscape as a soundscape with percussive events, and in the resynthesis, in the evaluation test of the product of the model, we did not cut off the resonances of the samples that were concatenated. We could have done so. We have some versions of the audio in which these resonances of the fragments were cut according to the duration of the resonances in the target sound. But we found more we found that this audio could illustrate a bit more how the samples were concatenated. But in the score, these they were transcripted just as it.
The shorter duration.
Yes.
Okay, thank you.
I actually, I don't have a question. I have a comment, but that may be a question as well. I found very nice this way of, I would say, machine transcription. This is very original work, because you are attacking a problem, the technomorphism, that is the writing of the instrumental synthesis. That is a kind of compositional, let's say, viewpoint. I would like you, if it's possible in short time, you express a little bit the importance of what you have done for this kind of composition, because you're making a kind of transcriptions. It's very original that. So that means you're moving from the sound domain to the score with a contribution. I think maybe I don't see too much in your presentation. How interesting is that for the contemporary music composition?
Yes, in that regard, Jose Padovani could say a bit more than me, perhaps, but in relation to the process that composed this procedure. But yes, for sure, I agree with you that this transcription of the product of this model is like a sketch, could be seen as a sketch in which a composer may work on and develop ideas that may develop into bigger or small or even experiment or just experiments, musical experiments, which may contribute a lot to a handful of creative processes. Padovani.
Yeah, so maybe I can say something really a general comment about this. The problem that we have in some tools like Open Music and other tools is that generally they limit the parameters of notation to pitch, duration, and dynamics. You don't have much that you can change in notation to specify a timbre or a kind of attack. And the tool that we use, that is Abjad, that is developed by Trevor Bacha, and it's a Python module. It allows to deal with notation in a very flexible way. And it was very interesting for this kind of project, that you don't want to notate just a pitch and a duration. You would like to notate much more. And so this is an aspect. And another aspect, maybe interesting, is that it's a creative approach to descriptors and automatic notation as a kind of algorithmic sketch. You don't want to classify timbres or to identify genres, but to use it as a really as a compositional tool to maybe plan an excerpt of a composition, or to plan something that can maybe use instrumental sounds and electroacoustic sounds. So it seems to be interesting. And also another aspect is that it's really open in the sense of open source, but also very open to change how things work, how you not only orchestrate, but how you deal really compositionally with this descriptor data. So this is very different from more ready-to-use tools like ORCID and computer-aided orchestration tools. So yeah.
I don't see anything similar. Congratulations. That's very interesting. So is there any question anymore? Okay. So I think we can move to the next paper. The next paper, I have to find the name, is Grain Birds, Evolutionary Granular Synthesized Distributed in Foggy Computing. Hello, everyone. I am Jonatas Manzoli from the Interdisciplinary Nucleus for Sound Studies and from the Arts Institute of University of Campinas, Brazil. I'm here to introduce to you and talk about the grand bird.
I'm Edelson Constantine. I'm from Interdisciplinary Nucleus for Sound Studies at the University of Campinas, and a great pleasure to be here to present this work with Professor Jonatas.
The article presents the grain bird concept inspired by a distributed fog of grain sounds metaphor. Shortly, granular synthesizers are distributed in a mobile device network, apply interactive genetic algorithm, and exchange open sound control messages in a virtual private network. Grain birds generated sound grains in standalone and network configurations. The Greenbird's concept dialogue with the Internet of Things paradigms, since it was inspired by cloud and fog computing architectures. In this sense, this article presents the Greenbird and Greenbird Orchestra concepts, followed by a review on computer music and network technology related to the project. The Greenbird app allows the generation and transformation of sound grains. It is explicitly controlled by a GUI and implicitly by motion sensors. The interactive evolutionary granular synthesizer implemented in Greenbirds comprise a population, a genome, and two genetic operators, crossover and mutation. As described in table number 1, there are 10 parameters to control the granular synthesizer. To demonstrate the interaction with mobile devices' motion sensors, we developed an improvisation test with 3 Greenbirds and a host GrainNet computer. We use 4 different devices, an iPhone, an iPad, and Moto G3, and a MacBook to test also compatibility between the app, different motion sensors, and iOS of these different devices. finally, Greenbird will be fundamental for developing the artistic research involving musicians and dancers, which motivated the development reported here. Thank you for your attention.
Thank you for your attention.
So any questions?
Could you talk more little about what is the possibilities for the user to use the app, if they can record sounds, how they can manipulate, etc.
So actually we use okay, we are using now the sounds you heard or bird sounds only to, let's say, to be explanative to the idea of grandbirds, but actually every user can record local sounds and manipulate locally. So that means the granular synthesize, it runs locally, as you saw. So every participant has a representation of the sound locally, but the message are sent to the host. So the host can also have a correlation or let's say orchestra combined by by people that is connected. So with that, actually the only reason we made that is because we are having challenges to teach in a discipline is called invenção contemporânea, contemporary creation, and we decide to help our students with a kind of device that can be used. So that means that's the reason. So, but I want to make it very clear. When you're talking about the orchestra, laptop orchestra, we have a Wi-Fi locally. Now we have a possibility of have a local Wi-Fi orchestra. We can have a distant connection, and also we have between the mobiles connection. So we have this whole set of possibilities.
Thank you.
Okay, Felipe, I never thought about that. That can be very interesting. How about to use that in the generation of games? It can be very, how about you try it? Because locally people, it's quite like a game, isn't it? The Grandbird itself, because people are participating of a performance. I never thought about that, but I think it could be done. I think it's a good idea, actually.
It's because we are actually here in UFPE, we have the discipline that is computational creativity, and one of the parts is using games. How can you procedural generate content inside the game? And we have a bunch of parameters that we can map. For example, the position of the player, or maybe some kind of mood that we want to make the player experience in that kind of sense. And I just thought that it's a very, very direct manipulation. For example, all the sensors inputs can be mapped to the player's input, or the character's input, or any kind of parameter that we would like to. That would be quite interesting to test in our discipline here, and also in discipline that Jebe minister here, that is lectures here, that is digital games. So just to make sure that we have the
we
connection.
did that. Zé Padovani asked about the artistic application. I want to comment because the original motivation 3 years ago, we had made a piece for dancers when the dancers were in the stage. So, and we interact with each other. So now we have the pandemics. So we decide to continue to make music with that people, with that group. So the original motivation that we are using now is the dancers, they are going to record their own sound locally, the sounds from their environment. So that they might produce a music in their own. As they record, they also interact with each other. So we have at least 3 instances of the music. That's what I want to try. We were trying now. We have the local music that's played by the device that can be recorded. When you interact, you send it to a second person in another position in the network. So these people receiving your message and also send to the host. So the host can also manipulate sounds that are independent in terms of sound because you receive only parameters and also produce another music. So, and our aim at the end, if everything goes well and the pandemic goes out, is to try that also in 2 situations. In a situation of having stage, when you have people combine the sounds in remote locate and other on the stage. And also we can have this application of orchestra of laptops, but not only with people locally using a desktop, but people remotely from somewhere using the mobiles and participating of the performance. I think the artistic application, I'm not sure if I'm answering your question, Padovan, because I have the idea of using that, but we didn't develop yet the work. We are working now with the dancers for trying to adjust it, to make it work.
Perfect. That's what I imagined. I wanted to know more about the context.
Yeah, it's the piece, you know, we had with Gabriel, so we had this. So we were trying to make a substitution of the accelerometers that we had a lot of trouble with the accelerometers, with the dance for the mobiles.
I think that it would be also very interesting for some kind of installation or something.
Exactly,
like
can be. But anyway, I think, no, great. So we were moved to the next. There's no question anymore. So let's go to the next.
Olá, meu nome é Eduardo Júnior e estamos aqui para o artigo Correlating Big Five Primary Personality Dimensions with Scripts, dos autores Luiz Moreira, que sou eu, Guilherme Cabral e Jordano Cabral. Atualmente existem N teorias para descrever a personalidade. Uma delas é a teoria dos Big Five. E o que é essa teoria, né? O que ela fala? Ela diz que a gente pode definir a personalidade em 5 fatores, que eu vou falar mais na frente. E para a gente definir essa teoria, a gente utilizou a API chamada Apply Magic Source, que com base nas curtidas das páginas do Facebook, a gente conseguia retirar essa informação do Big Five. E aí, um estudo realizado pelos desenvolvedores diz que ela é capaz de prever com mais assertividade que a prever sua personalidade. E aí vamos agora quais são os 5 vetores, né? 5 características de personalidade. Openness, a primeira delas. Então, quanto mais positiva a pessoa tende a ser aberta a novas ideias, mais curiosa, imaginativa. Quanto mais para o negativo, ela tende a preferir, ela é uma pessoa mais prática, prefere rotinas. A outra vertente é conscienciosidade. Então, mais positivo, hard work, mais organizada. Negativa, é uma pessoa mais impulsiva ou desorganizada. Extroversão, positiva, é uma pessoa mais calorosa, busca novas aventuras. Menos é uma pessoa mais reservada, mais quieta. Amabilidade. Então, quanto mais positiva, ela ajuda mais, é uma pessoa mais confiante, mais empática. E ela, negativa, é uma pessoa que tem mais suspeita, ela gosta de cooperar. E por último, neuroceticismo, quanto mais positiva a pessoa tende a ser mais ansiosa, mais negativa, ela é mais calma, mais segura, mais centrada. E aí a gente faz essas relações das características de personalidade, das características musicais. Para isso, a gente contou com a ajuda do Spotify para coletar a música dos usuários e extrair as características das músicas. Das características foram coletadas 8 características, que são elas: acusticidade, dançabilidade, para definir o quanto a música é dançante, energia, que representa o grau de energia da música, se a música é instrumental ou não, se a música ela é ao vivo ou não, o tempo, representado geralmente ali por batida por minuto, valência e popularidade. Esses 8 aspectos, eles juntos. E aí, o que a gente fez? A gente criou uma aplicação que a gente pudesse coletar essas informações e realizar a análise. Então, a aplicação, a gente tem o login do Facebook e o login do Spotify. Então, nós coletávamos esses dados a partir do Facebook, juntávamos todos eles numa base de dados. Com isso, processávamos no Python, coletava as características no Spotify e API, rodava tudo no CSV, analisava no R e gerávamos alguns gráficos e análises. Beleza, com isso a gente vai para os resultados e é que a gente vai falar um pouco sobre quais foram as principais correlações. Então, do uso da aplicação, basicamente, os questionários de Big Five, eles tendem a ser muito longos. E é que, só coletando a página do Facebook, a gente teve uma celeridade maior em preencher isso. Os participantes, a gente teve 31 participantes válidos, onde foram 16 mulheres e 15 homens, com a média de 32 likes. E aqui a gente tem quais são as principais correlações. Então, quanto mais extrovertida a pessoa é, ela tende a gostar de músicas mais populares, com o quadrado ali, vocês podem ver. A correlação negativa nesse caso entre valência e openness. Então, quanto menor for o openness, maior é a valência da música. Então, isso a gente pode ver ali de pessoas que são abertas à experiência, elas tendem a gostar de músicas menos positivas. E dançability e extroversion. Quanto mais extrovertida a pessoa é, maior é a dançabilidade da música. E aí, por final, a gente tentou realizar uma regressão linear com todas as características. E aqui a gente teve melhores resultados foi com dançabilidade, onde a gente fez ali com 3 features, e com duas a gente acabou achando que teve um resultado melhor, onde, para explicar a dançabilidade, a gente usa um conjunto de extroversão e amabilidade. Trabalhos futuros, a gente quer basicamente enriquecer esse trabalho com a letra das músicas para ver qual o sentimento da música em relação, se não tem. E é isso, gente. Dúvidas? Obrigado.
So, I'm so sad because it's the last paper and I want to be with you for more time. So is there any question about the last paper? I want to make a question, maybe because I read the paper very fast, so maybe I didn't get it. But when you're talking about the descriptors you use to qualify the music, I'm not sure if I understood the way you are extracting these features from the material, from the audio. How it is done?
Opa, Jantas, boa tarde. Estava aqui desde o iníciozinho, vou responder em português.
Sim, claro.
Prazer em conhecer. Claro. Tá, eu vou até combinar com o Johan. Cara, tua energia é muito massa. Desde ali do início, prazerzão tá por aqui te acompanhando, não conhecia. Mas, então, as características que a gente usou foram disponibilizadas pela Spotify, o API, que é um trabalho, se eu não me engano, do Tristan, que vem da Econest, que foi comprada pela Spotify, que ele caracteriza ali e entrega para a gente essas 8 features, né? Dançabilidade, se a música é instrumental, se é ao vivo, se não é. Então, a gente acaba usando essas características e faz essa relação. E aí, para pegar base de dados, né, para construir essa base de acordo com cada um dos usuários. A gente pegava as músicas recomendadas para eles e aí fazia um wrapperzinho, um scrap no Spotify para pegar essas 8 características. Então, basicamente, era uma API, e aí tem algumas ferramentas da própria Conest, do artigo também, que eles entram um pouco mais a fundo de como é que é feita cada uma delas. Mas aí cada uma dessas características tem um jeito particular de se extrair. Algumas olham para o MFCC, outras olham para a questão do tempo ali, batimento. Então, cada uma tem uma forma diferente de se extrair. Então, basicamente, é esse o processo, né? Na minha aplicação, a gente olha só para o consolidado, já para o valor ali, geralmente entre 0 e 1, de cada uma das características.
Legal. Tem mais alguma pergunta, gente?
Vou perguntar para o Delano, que aquela segunda característica, acústico, seria unplugged, coisa desse tipo? Ou...
Isso. Tá muito relacionado com o tipo de instrumento ali que está sendo usado.
As sonoridades, né?
Então, é a sonoridade, de fato.
E se tem distorção, aí já não é acústico, né?
Isso. E aí, a gente está com o tempo, acho que bem estourado, mas uma coisa legal, tipo, para
eu não acho que a gente está com o tempo estourado. A gente devia ficar a tarde inteira aqui.
Você que manda, né? Então tá de boa aqui. Então vamos seguir. Existem alguns pontos interessantes que, tipo, pela facilidade de se extrair essas métricas, a gente consegue fazer uma relação com vários trabalhos, né? Tipo, minha vontade de trabalho futuro é olhar para as letras da música. Então, a gente tem ali um grau de valência da música, né? Que descreve a positividade, que está mais relacionado à instrumentabilidade, né? A música da coisa. Mas será que a letra acompanha esse repertório? Será que a letra também existe um grau de positividade, existe um sentimento mais sadness ou positivo com relação a isso? Então, existe uma série de trabalhos futuros que a gente pode trazer nesse contexto, né? Então, o que é que dá para juntar aqui? Pegando todo esse conceito de MIDI, música, e incorporando também a parte de NLP, né? Fazendo uma análise disso e cruzando essas duas fontes de dados. Então, são alguns planos que dá para fazer aí, reaproveitando essa base, reaproveitando essa mesma aplicação e só acrescentando mais um legozinho, feito alguém falou em algum momento agora.
Mais alguma pergunta? Gente, a gente vai terminar. Eu tô com dor no coração. Será que a gente não podia abrir a câmera todo mundo aí para fazer uma fotona aí, velho? Pô, gente, ó, beijo pra vocês.
Eu tô que nem o Diogo na última sessão, muito com legal. Criança no quarto, tentando cuidar para não...
Não, mas de todo jeito a
Vou
gente
ficar
tem
aqui
que...
no breu, só na luzinha, cadê?
Valeu, gente. Bom
revê-los.
Sérgio, a sua voz de narrador de alcova é maravilhosa. Eu vou pro próximo paper que eu fizer, vou pedir para você narrar. Valeu, gente. Valeu. Muito bom, gente.
Valeu. Parabéns, pessoal.
Valeu, Felipe. Valeu, Júlio. Aí, gente. Fiquem em paz. Eu vou ficar por último. Vai saindo aí. Valeu, pessoal. Valeu. Tchau.